Okay, sorry for being a little bit late. I'm sort of in the middle of all this probability stuff. I've pretty much finished chapters 13 and 14 in terms of the content, but I wanted to go back a little bit and do some more examples, and then get on to chapter 15. So just to remind you, thanks. I'm just going to write down briefly what the tools and rules are that we've done. So these are just kind of ways that you might solve probability problems. Oops. Yeah. So the first is equally likely outcomes. If all the outcomes are equally likely, you can just count number of ways something happens divided by the total number of possible outcomes. I guess I'll write that. So number of ways an event happens divided by total number of possible outcomes. That's a way of solving a probability problem. The second thing is complements. So the probability of an event is 1 minus the probability of its complement. So this is essentially 1 minus the probability it doesn't happen. And just a quick little picture of that to remind you. This Venn diagram represents everything that could happen. So it has total area 1. So the area of the circle is 1 minus the area outside the circle, basically. OK. So then multiplication rule. Says that the probability of A and B is equal to the probability of A. And it doesn't really matter which event you do first. Okay? You could start with B and then do the other one, or you can start with A and then do the other one. Okay? So I sort of view this as needing to overcome both hurdles. Both these things have to happen. So you can sort of think about what proportion of people the first event would happen to, and then of those people, so given that A happens, what proportion of those people would you expect to have B happen to them? So that's sort of the way I kind of think through that probability. So you read this as probability of A times the probability of event B given A. So this vertical line is given. And this is often referred to as a conditional probability, meaning that there's a condition, right? It requires that A happens. So I don't know. I sometimes think of this as living in a universe where that is just true. I know it's true. It's already done with. Now I just need to worry about event B. OK, so then addition rule I did kind of at the end of the lecture. Probability of A or B. So this is not as restrictive, right? If I have probability of A and B, that requires both events to happen. So one way you might kind of differentiate these, sometimes people say, like, OK, should I add them or should I multiply them? Well, A and B is more restrictive. And so when you multiply two probabilities, it's going to make things smaller. Probabilities are always between 0 and 1. So making something more restrictive is multiplication. A and B, more restrictive. A or B, well, that could happen in either way. So that should be kind of less restrictive. If A happens, it happens. Or if B happens, it happens. So that's kind of suggests addition. So we have probability of A or B. You have to subtract the probability of A and B. OK? And the picture I drew for that, I'll stick it on here. OK, so I want this whole shaded thing everywhere where A happens, everywhere where B happens, and also including where both happen. So I draw that picture to kind of illustrate that it's not just adding the A circle to the B circle. You sort of think about probabilities as being areas in Venn diagrams. And you can't just add those two circles together because that would count the stuff in the middle twice. So we do want to include the stuff in the middle, but we only want to include it once. So subtracting the probability of A and B avoids double counting. Okay? So I'll talk a little bit more about that idea today. And then after I do that, I'll do the fifth thing. So I haven't talked about this one yet, but it's called the binomial. So this is today. And in your book, that's in chapter 15. These first four are a little bit interspersed throughout chapter 13 and 14. It's not quite, chapter 13 and 14 are not quite organized step by step this way. So when you read through your book, you sort of treat 13 and 14 as just being about probability, and all these are in there somewhere. I mentioned last time that the addition rule, the way it's given in the book, doesn't have this, and I'll say why now. Okay, so according to the book, and this isn't wrong, it's just not complete. According to the book, if you want to find A happens or B happens, check to see if they are mutually exclusive. If they are, add the chances. Okay, so I think of this as a special case of the addition rule. Okay, so the way that I would think about this is that, oops, these are actual white one. It's yellow too. I think I have a white one. The white ones and the yellow ones actually look very similar. It's kind of, for some reason, they coat the white ones in yellow a little bit. So, sorry. So I say, so a special case of the addition rule is this. So if events A and B are mutually exclusive, then you can do this. Okay? So remember the reason why in the addition rule, the reason why we subtract this is to avoid double counting. Well, mutually exclusive means that it looks like this. Okay? Mutually exclusive means this. So there's no problem with double counting. Because the probability of A and B is 0. Right? So you could just happily use this full form of the addition rule, go about your business, probability of A or B, figure out probability of A, figure out probability of B, and then when you get to the point of trying to figure out probability of A and B, well, if they're mutually exclusive, hopefully you recognize, well, those two events can't both happen, the chance of that is 0, so you don't have to subtract anything. So in a way, you don't have to really worry too much about the definition of mutually exclusive or the idea of mutually exclusive if you're just solving probability problems. Okay? just in terms of your education, I think you should know what mutually exclusive means, this idea. And I think you should also know what independence means. So I talked about independence a little bit last time and how that leads to a special case of the multiplication rule. All right, so just to contrast those. Just write this again. So these two things, these two topics, mutually exclusive, independence, special case of the addition rule, special case of the multiplication rule, these two topics are not really related. The reason I'm talking about them next to each other is because often people think that they are somehow related, and so I just want to kind of highlight the differences between them. Okay, so that's why that's why I'm talking about them next to each other. So the special case of the multiplication rule is that if you want probability of A and B, and A and B are independent, you can write probability of A and B is equal to probability of A times the probability of B. And what does independence mean? Independence means the probability of B given A is equal to the probability of B. You can write independence in a few different ways, and I sort of talked about this last time, that basically you can write it this way, or you could write it as the probability of A given B is equal to the probability of A. Okay? And actually there are a few other ways to write it, but that's basically the main two ways to think about it. So in English, what this means is that the probability of B is not changed, or is not dependent on whether or not A happens. Okay, so probability of B is something, and then if event A happens, that doesn't change the chance of B, right? The probability of B given A is the same. So the general case of the multiplication rule says that the probability of A and B is equal to the probability of A times the probability of B given A. Well, this, if they're independent, is just the probability of B. So that's why we get this special case here. OK, so just to highlight the different, any questions about this? Questions, anything come up for you? OK, so just to highlight the contrast between these two properties, independence and mutually exclusive, if they're independent, then you know the probability of A and B is equal to the probability of A times the probability of B. If they're mutually exclusive, the probability of A and B is 0, right? So you can't have two events that are both mutually exclusive and also independent unless what? Anyone see it? How would it be possible for this to be true? Probability of A and B equals the probability of A times the probability of B. How could that be true and also have this be true? Yeah. Sorry? That's right. If either of them has probability 0. Okay, so she said if they're impossible events. So if probability of A is 0, then this product will be 0. They'd be mutually exclusive. If B has probability of 0, also true. The product is 0, and they're also mutually exclusive. So that's sort of impossible. It's by definition an event that will never happen, and we don't really care about it. Okay. So for for all practical purposes in this class, if two events are independent, they won't be mutually exclusive. If they're mutually exclusive, they won't be independent. Right? There's this sort of mathy counterexample if either of them has probability 0, but it's a little bit silly. Sort of by definition, they don't happen or they can't happen. OK? So any questions about that? Yeah. what does independence look like? Well, I don't think there's a picture of independence that is as, I don't know, as useful to draw as that. The picture I'll draw is essentially a Venn diagram for two die rolls. So say we have two dice, red die, blue die. And we have the possible outcomes 1, 2, 3, 4, 5, 6. And so the two dice are independent, right? The red die and the blue die are independent. When I say the dice are independent, what I really mean is that any events having to do with those two dice, like any event having to do with red and any event having to do with blue, have to be independent, okay? So here, when I define independence here, I'm really talking about independence in terms of events, right? So when I say independence of the red and the blue die, what I mean is that any events that I could make with red and blue are going to be independent. OK. So let's say the event A is red equals 6. Event B is blue equals 6. So those events are independent. And if I draw those in the picture, this is where the red one's 6. This is where the blue one's 6. OK, so thinking kind of geometrically about this statement that the probability of B given A equals the probability of B, well, the probability of B is 1/6, right? It's this. OK. And in terms of the area, you can sort of see, right? This is 1/6 of the total area. So you might think of that as being equal to 6 out of 36. There are 36 possible outcomes in this whole Venn diagram, and 6 of them, 1, 2, 3, 4, 5, 6, are where the blue die is 6. I mean, you could just think about the blue die all by itself and not worry about the red die and just think about, OK, 6 possible outcomes for the blue die. One of them is a 6. But I sort of want to think about it this way to compare this with the probability of B given A. Now, intuitively, you sort of have this idea that it doesn't matter what happens with the red die. The chance the blue die is a 6 is still going to be 1 out of 6. OK, so that's fine. But in terms of trying to figure out what this means in the picture, this is restricting ourselves to a universe where event A has happened, right? That's the idea of saying given A. So it's essentially restricting ourselves to this part here, right, where the red die is a 6. Event A has happened. So I sort of think about this as being like, I mean, it is 1/6, but I think of it as being like this, right? This is both 6s. And on the bottom is this part here, where this is where red is 6. OK? So that's the picture I'm going to draw. And I just, to sort of try to make it clear what's going on with this probability, I'm drawing this little picture to illustrate that we're in a universe where event A happens. So it's as if we ignore everything up here, right? I know, as if I've already rolled the red die, I've gotten a 6. And of the different ways the red die could be 6 in this universe, 1/6 of those things are where the blue die is also a 6. Okay? So that's kind of the way I think about this in terms of the picture. And it is a little bit hard to draw the picture in a way that makes sense. So that's why I didn't do it originally, but that's the picture. Okay? Any comments on that or further questions? OK, so I just wanted to go back a little bit and go back to the addition roll and the multiplication roll. I think those two are the most, I don't know, maybe most confusing. People get confused about those things. In general, when you see and, think about multiplying. When you see or, think about adding. If you don't see either of those words, you might try to think if you can rework the problem in order to get the word and in there or get the word or in there. And then I also wanted to talk about these special cases where if they're mutually exclusive, the probability of A or B is just the sum of those two probabilities. And like I say, in the book, that's the only case they really deal with. In the book, they don't give that full form of the addition rule where you have to subtract the probability of both. But I feel like it's not that much more to just give it to you. And then this idea of independence and the special case of the multiplication rule. OK? Everyone good? Questions? Any of that? OK, so let's do a couple of examples. So the first one I'm going to do is to suppose I have a drawer with 4 green socks and 6 red socks. It's my special Christmas sock drawer. And I suppose that they're all mixed up. They're not matched together in any way. And I pick 2 socks in the dark, or maybe if you imagine I'm colorblind, I can't tell the difference between red and green, whatever. So pick 2 socks at random. And find the probability that they match. Okay, just meaning that they're the same color. Okay, so the find the chance I get 2 green or 2 red is one way to think about that. So yeah, so find the chance they match. I was illustrating in what I hope is a kind of relatively simple example. When you see some event like this where they match, I think your mind immediately starts thinking, well, how could that happen? How could it be that they match? And hopefully you see that they could match either if they're both green or if they're both red. So this is a fairly common technique to break up an event into the different ways that it could happen. So this is probability both red or both green. Okay, so again, I don't know, sort of 2 ways to get to this point. One way is that when you see match, you might think of this idea that I said a little bit earlier, which is that if you don't see the word or anywhere, you don't see the word and anywhere, you might try to think about, is there any way that I can reword this statement to get the word or in there? And once I see the word or, then I can apply the addition rule. Another way to say that, or another way to sort of go from this to this, is to think, whenever you see some kind of complicated event, well, what are all the ways that could happen? It could happen if they're both red or if they're both green. If I had more colors, like 4 green socks, 6 red socks, and 8 purple socks, well, they could also match if they're both purple. So then I need to sort of add in another term, both red or both green or both purple, right? OK, so this one, both red or both green. Well, you could just start doing it, right? You could sort of apply the addition rule. So I'm going to write this both red. I'm just going to abbreviate it as RR, plus the probability of both green. And the addition rule says I should subtract the probability of both of those things, right? So then you sort of think, is it possible to get both socks to be red and simultaneously for both socks to be green? No, right? So you know the probability of both those things is going to be 0. So if you're just kind of thinking addition rule, you see like A or B, you think, OK, I want to add the first one to the second one, and then subtract the chance that both red and both green can't happen. It's 0, so you can ignore that. As you gain more experience, I think the way that you think through that process is that when you see this problem, you think, oh, those are mutually exclusive. Done. OK? So, like I say, if you just sort of blindly apply the addition rule, you get the right answer, no problem. As you gain a little bit more experience, you sort of maybe jump a little bit faster to the idea that, oh, those are mutually exclusive. I just add those chances don't worry about the probability of the intersection. It's 0. All right, so probability of red, red. What's that going to be? What's the probability they're both red? Anyone? Yeah, sure.
The first one is red and the second one.
Yeah, so this is you. If you want to translate this in English, you can write this as the probability of first red and second red plus probability first green and second green. Okay? So your thought process here is that you have this event both red, or if you write it RR, that's fine. And trying to write that in a way that will allow me to use the word and. Okay? Once you think and, or maybe you think, jump immediately to the math. I'll just squeeze this in here since I'm almost done. What is this going to be? First red, probability of first red times the probability the second one's red given the first one's red. Right? So what's that? First red is 6 out of 10. What's the chance the second one's red given the first one's red? 5/9, good. So are these two events independent? These two events? They're not independent, right? The chance of getting the second one to be red depends on whether or not the first one was red, right? OK. And we can add to that 4/10 times 3/9. Sorry, it's all squished, but I don't feel like going all the way over there. So this is 30 plus 12 is 42 over 90, which is 7/15. OK? OK. So if you left your answer like this on a test, that would be OK, right? You just leave it in this form. I don't really care. Like I said before, for probability problems, it's sometimes nice to see what you're thinking. If you got the wrong answer, it'd be easier to grade if this was on the page, right? Like if for some reason you had, I don't know, 6/10 times 6/9, then it's clear that you forgot to remove that sock, or 6/10 squared, 6/10 times 6/10, sort of clear that you were treating them as independent or something like that. Easy to see what's going on. If you just write down an answer, then it's kind of hard to figure out what to give you. OK. Any questions on this? OK. So let's do one more that sort of is similar, but different. Actually, I'll use that. I'll use that as a continuation. Actually, I forgot my cards. I was going to do a problem with cards. I guess I'll just do it. You can imagine my cards. So I have a standard deck. And I want to find the probability. Second card is a spade. I actually did this last time. Just intuitively, but I wanted to do it again, doing a little bit of math. So there are 13 spades in the deck, 52 total cards. So the answer here is 13 out of 52. I'll just tell you, right? When I talked a little bit about this last time. If you remember the red, white, blue little piece of paper we played with last time, I talked about the chance the second pick is white, right? And said, well, that better be a third, because out of the class as a whole, about a third of you should get the second one to be red, about a third of you should get the second one to be white, about a third of you should get the second one to be blue. No, all three of those are kind of, there's no reason why one should be more likely. They're all equally likely. And that's a little bit hard to see sometimes, because for your individual experience is that if you got the red one first, well then for you the chance the second one is white is a half. It kind of feels that way anyway. But if you just think about what we mean by probability second white, it's like what long run proportion of people do you expect to get the second one to be white? It's not you. It's sort of like in general, you know, out of lots and lots of people, what proportion should get the second one to be white? Another way to think about it is if you do want to think about it in terms of your personal experience, you do have a 1/3 chance of getting white before you do anything. And when I say probability second one is white, I'm not saying given anything. I'm not saying given the first one's red. I'm not saying given anything. So essentially, you are thinking about that probability without taking any other information into account. What happened to you on the first draw, whatever. Same thing here. All 4 suits should be equally likely: spades, diamonds, clubs, and hearts. So since all 4 suits are equally likely, you should think of this as being 1/4, which is 13 out of 52. Another way to think about it is that I'm not conditioning on anything. I'm not given any information. So without knowing anything about the first card, well, really, the second card could be any one of the 52 cards in the deck. And every one of the 52 cards in the deck is equally likely to come up second, right? You shuffle a deck, stick it in front of you. Any one of the 52 cards in the deck could be second, okay? There aren't any cards that excluded. You know, you might sort of think, well, whatever the first card is excluded, you know, whatever that first card is, that can't come second, but we don't know what that is. So we can't exclude any of the actual, you know, cards from coming up second. And just to sort of further that logic, you know, I can give you, sort of fan the cards in front of you and say, pick any card. Pick the 10th card, the 20th card, the last card, whatever. The chance that card is a spade is going to be 13 out of 52, or 1/4. Okay? Nothing special about the second card or any other card. Each one of the cards has a 13 out of 52 chance of being a spade. Okay, so that's just talking, right? I did want to do a little bit of math. But any thoughts or questions about any of the stuff I was saying? Kind of trying to talk about this intuitively. Okay, so I'm going to employ sort of the same logic I did over there. How can the second card be a spade? So the possible ways to get the second card to be a spade, I think when you see that event, your mind sort of naturally thinks, well, it sure would be nice if I knew what the first card was, right? So, or you might think, you know, well, it depends on what the first card is, or something like that. I think the first time you see that problem, or your first reaction to that problem is that, well, I don't know what the first card is, okay? So let's think about what the first card could be. It's going to be either a spade or not a spade. So one way to write that, and notice I said the word or there, right? One way to write this is to think about how this event could happen depending on what happens with the first card. So this is the probability of getting first spade and second spade, or first not spade and second spade. Okay. So again, I'm employing this logic of thinking about, well, how can I divide that event up into these different parts? This part or that part. Okay, any questions about that? Okay, so I could just start using the addition rule and go ahead and think, okay, probability of this plus the probability of this minus the probability of both. Are these two events mutually exclusive? These big events, this event, are those two things mutually exclusive? Yeah, they are. A few people were nodding. Because in this case, the first one's a spade. In this case, the first one's not a spade. So there's no way for this first card to simultaneously be a spade and not a spade. So these two big events, these whole things, are mutually exclusive, right? OK, so we can just jump to the special case of the addition rule. Like I say, if you just kind of apply the addition rule, start out doing things, you sort of fall into, hopefully at the end, recognizing that that last thing is 0, so you don't have to worry about it. But you know, if you recognize they're mutually exclusive, you can just start out thinking about this problem as a special case. OK, so first spade, 13 out of 52. second spade given first spade. I'm not going to write out the full multiplication rule, but it's this times the probability of second spade given first spade. So if we know the first one's a spade, we've taken out one of the spades, we've taken out one of the cards, so that's going to be 12 over 51. And then we're adding on first one not a spade. There are 39 non-spades in the deck. So we got one of those 39 non-spades. And once you take out one of those, there's still 13 spades left, but there are only 51 cards left. Now if we add those together, I'm going to factor out 13 out of 52 from both of these. So there's 13 out of 52 here, and there's 13 out of 52 here. You'll see why in a sec, I think. So that leaves me with 12 over 51 plus 39 over 51. Okay, so the reason why I did that, the reason why I factored out the 13 out of 52 from each is that these add up to 1. 12 plus 39 is 51 divided by 51. So this goes away, and I just get 13 out of 52. Okay, so that's the answer that I argued intuitively should be true. But I wanted to do the math, okay, just to sort of go through the problem and see how that works. And again, this is very similar to the SOX problem. We're taking this event, second card is a spade, and dividing it into the ways it could happen. This gets pretty messy once you get to like third card, fourth card, right? If you want to think about all the different ways the third card could be a spade, depending on what the first two cards are, you're going to have to go through, well, you have to go through 4 possibilities. The first 2 cards could be like spade, 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 not a spade, spade, or not a spade, not a spade. So if you wanted to, you could sort of go through all that and add them all up and do it, but I won't bother. OK? You get the same answer. Probably the third card is a spade is 13 out of 52. Probability the 10th card is a spade is 13 out of 52. Okay. Questions on this? That idea? Either the intuition or the math? OK. So I just want to, well, maybe I'll write it out. Sorry, I want to write out one example I did last time, but kind of rushed it a little bit. So just remind you of the full use of the addition rule. And the reason why I want to do this is that both of these examples I did were with mutually exclusive events. So I want to do one more example where they're not mutually exclusive. So I'm just going to repeat from last time. I want to find the probability of at least 1/6. So like I said, I did this last time, but I want to kind of revisit it because I think it's a nice example. One way to do this is just by counting equally likely outcomes. Okay? So 36 possible equally likely outcomes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the answer is going to be 11 out of 36. Another way you can do that is to think of this as being equal to, so this is method 1. So method 1 is 11 out of 36 by counting. Method 2 is to say that this is equal to 1 minus the probability of no 6s. So this is the chance that the first one's not a 6 and the second one's not a 6, or the red one's not a 6 and the blue one's not a 6. 1 minus 5, 6 times 5 sixths. 5 6 times 5 6 is 25 over 36. 1 minus 25 out of 36 is also 11 out of 36. And the third way is to use the addition rule. So this is the part I really wanted to repeat. Is to say that this is equal to the probability the first one's a 6 or the second one's a 6. Or red 6, blue 6, whatever. Actually, I'll do it with red and blue. Red 6 or blue 6. Okay. So the same events that I was talking about that independence example there. So this is probability red 6 plus the probability blue 6. And now these are not independent, or sorry, they're not mutually exclusive. They are independent, but they're not mutually exclusive. So we have to subtract the probability of red 6 and blue 6. Red 6, 1/6. Blue 6, 1/6. Okay? We can't stop there because they're not mutually exclusive. Red 6 and blue 6 is 1 out of 36, or 1/6 squared. Okay, so they are independent, so I can just multiply 1/6 times 1/6. So that again comes out to be 11 out of 36. Okay, so I just wanted to do one more, or go back to this one where you do have to deal with the minus the probability of both. Okay, so any questions on that? Okay, so I'll consider that to be sort of the end of chapters 13 and 14, and the end of the first 4 items. Take a little break, and then I'll do the binomial formula, which is chapter 15. Okay, it's fairly short. So the binomial formula is chapter 15. And it's used for solving a very specific kind of problem. Okay? So to sort of, before I give you the formula and tell you exactly how to use it, I want to go through kind of building up some stuff that leads to the formula. So I want to talk essentially about counting. So part of what the binomial formula does is kind of a sophisticated way of counting things. And a lot of it's about permutation. So what I'm going to talk about, if you've heard about permutations or used them somehow, is about that. So the example I like to start with is with 3 people. And I'm going to kind of use their initials, but I'll give them names. Alice, Betty, and Carl. So I'll just kind of refer to them as A, B, and C, but it's nice to give them sort of an identity. So what I'd like to think about is how many different ways can I put these 3 people in different orders. So you might imagine there are 3 chairs. How many different ways could they sit down, basically? So one way is that they go A, B, C. Another way is that they go A, C, B, or B, A, C, B, C, A, C, A, B, and C, B, A. So the way I'm organizing this in my head is I'm sort of sitting one of them. So I'm sitting Alice first. And then if I sit Alice first, well, Betty could be next and then Carl, or it could be Alice and then Carl, then Betty. Okay? And then if Betty sits first, either Alice, Carl, or Carl, Alice. And then if Carl sits first, either Alice, Betty, or Betty, Alice. Okay, so that sort of gives me a list of all the different ways that I can do it. Like I say, I sort of organize in my head based first on who sits first, and then who sits second, who sits third, and then the next person sits first, and so forth. So this sort of, I don't know, makes me confident that I've got every possibility. So this is 6, and this is often written 3 factorial. So you read that as 3 factorial, not 3. Thanks. I'm always afraid no one's going to laugh when I say that. OK, so that's 3 factorial. And it literally means 3 times 2 times 1. OK, so when you see the factorial, the exclamation point means take that number and multiply down by 1, 3, 2, 1. OK, so one way to think about why that's true is, well, there are 3 choices for who sits first, either A, B, or C. And then every time you sit someone first, there are 2 choices for the next person, and then only 1 choice left for the last person. You can see, hopefully, if there were like 5 people, well, you have 5 choices for the first person. And then once you put them down, there are 4 choices for the next, then 3 choices, then 2 choices, then 1 choice. It's natural. However many people you have that many factorial number of ways of sitting them all down. OK, so now suppose we don't care so much about the actual people, but just about their gender. So I'm supposing that Alice and Betty are female and Carl is male. So then let's think about how many different ways could we mix that up. So suppose and I'm restricting myself to just, two genders. So we have female, female, male. How else could it happen? Well, it could be female, male, female, or it could be male, female, female. Okay? So that's only 3 ways, right? So I want to think a little bit about, well, what's the relationship between these two things? So female, female, male is like these two. These two, female, female, male, female, female, male. So this is FFM. Okay? And then what about the next one? Female, female, male, female. That's these two. Female, male, female. And then the last two are male, female, female. So there's this relationship that these, this one, the ABC and the BAC, kind of collapse into one thing when I just consider gender. And so one way to think about the number of ways that this could happen, I mean, it's 3, we can just count it. But this is equal to 3 factorial divided by 2 factorial. And I'm going to stick a 1 factorial here. 1 factorial is just 1. But I want to think about this as this 2 represents the number of females. And this represents the number of males. And this on top represents the number of people. So why is that the right thing to do? Like I said, in this example, it's dividing by 2. Well, why do I think it's 2 factorial? Well, 2 factorial is the number of ways of mixing up AB and BA, right? So there are 2 ways to mix up those 2 women. Now, if there were 3 women, and I made some longer list of like 3 women, 1 man, well then in the list of 3 women, there would be 3 factorial ways of mixing up those 3 women that would all look the same in terms of like FFFM, right? If my 3 women were, I guess let's say Alice, Betty, and Dorothy, I'll throw a D in there instead of just, make another one. Then the ABDs, there would be 3 of them, and any way that I mix up the ABDs would look like FFFM, right? So if I have ABDC, or ADBC, or DABC, or whatever, there are 3 factorial ways. There would be 3 factorial ways of mixing up those 3 women that would all look the same in terms of my list of just the genders, okay? So that's why I need to divide by that 2 factorial. And in general, it's however many women there are, I need to divide by that factorial, because that's the number of ways of mixing up that many females that all look the same, right? Like they give you different elements here. So in this 3 factorial list, there are, well, in this, again, in this specific example, there are 2 different ways of having these, but you think of this as 2 factorial, the number of ways of mixing up the AB, BA. So in this long list of 3 factorial, I need to divide by that because that many things all look the same in terms of the genders. Okay, so questions about that idea? Okay, so that's a little bit of a counting thing. This is sometimes called choose. So I'll write it out just for this example. I guess I'll just say this is often written 3 choose 2. Because another way to think about this why this is the way it is it's the number of ways of choosing 2 objects amongst 3. Okay, so if you think about, so in a sense, some people think of this as not caring about order. If I have these 3 people here, and say they're the 3 people here, like in the front row here, and I ask 2 of them to come up and stand on stage, and don't worry, I won't make you, then how many different sets of 2 people could I make? Well, I could choose Alice and Betty, I could choose Alice and Carl, or I could choose Betty and Carl. There are 3 different ways for it to happen. So that's the same 3, okay? It's the same it's a different way of thinking about it, but it's the same idea. If you want to think about how that relates to the F's and the M's, you might think of that as choosing 2 of them to be female and 1 of them to be male, okay? Or maybe choosing 2 of them to make them wear a hat or whatever. You know, labeling 2 of them one way, and then the other one is labeled the other way. Okay, okay, so that's my counting thing. Now, I want to think about a probability question. Suppose I flip a fair coin 3 times, and I want to find the chance that I get exactly 1 head. Okay, so I have these 3 coin tosses, find the chance I get exactly 1 head. So not doing this as a chapter 15 problem. If you didn't know, I'll explain how to think about this as a chapter 15 problem. But if you just sort of saw this problem, I think a natural way to try to approach it is this same idea that I was doing with the addition rule here, with this find the chance the second card is a spade. And to think, well, what are the different ways this could happen? How could I get exactly 1 head? I could get exactly 1 head like this. If these are my 3 coin tosses, I could get a head and then 2 tails. Or, well, the head doesn't have to happen first. It could happen this way. Head could happen second. Or it could happen like this. Okay? And, well, what's the chance? So first of all, you notice that these are all mutually exclusive. They don't overlap, right? If this happens, then there's no way that this happens. There's no way that this happens. Okay? So I can just happily add them up. It's as though, you know, it's with 3 events, but it's as though you have this, and you want to find the total area of all 3 circles. They don't overlap, so you can happily add them up. And the chance of getting heads and tails, that's a multiplication idea. So 1/2 is the chance you get heads, and then tails, and then tails. Okay, so 1/2 cubed plus 1/2 cubed plus 1/2 cubed. 1/2 cubed is 1/8, so this is going to be 3/8. You actually, it is 3/8, but let me just write it a different way just for illustrating something. You could think of it as 3 times the chance of one of these things. So I'll write it that way. 3 times 1/2 cubed, that is 3/8, okay? But if you think about it this way, there's a relationship between this problem and that, right? That the number of ways of mixing up 2 F's and an M is the same as the number of ways of mixing up 2 T's and an H, right? So when I make this list here, I sort of know there are going to be 3 items on it if I've thought about that, okay? So let's think about what happens if I make this. So any questions, I guess? Any questions before I do something harder? Everyone okay with this? Okay. So like I say, you could think about this as counting the number of ways of mixing up the 2 T's and an H. So I'll just say number of ways of mixing or permuting those 3 things. And this is the chance of 1 sequence. Okay? These 3 sequences all have the same chance. So if we just multiply the number of ways of mixing them up times the probability of one particular sequence, then we get the right answer. Okay, so Let me do one that's a little bit harder, but I think still pretty manageable. Roll a die 5 times and find chance of exactly 2 6s. Okay? So I'm going to basically use the same logic. Now, I don't really want to write down a list of all the ways of basically mixing up 2 6s and 3 non-6s. I'm going to do it, but in general, that's sort of not the best way to approach the problem. I'd like to sort of use this logic to try to think of, well, can I do this by the number of ways of mixing them up times the probability of one particular sequence? I'd like to do that, but I'm going to kind of do this one the long way. So when I think about this, I will make that list. So 6, 6, not 6, not 6, not 6. That's one possible way for this to happen. Okay? So it's the probability of that. Or, well, I'm going to keep the first one as a 6 and then move this other 6 to all the possible spaces. So I have 6, not 6, 6, not 6, not 6. Right? Keeping that 6 there, moving the 6 over. Or 6, not 6, not 6, 6, not 6. Or 6, not 6, not 6, not 6, 6. Okay? So that's a list of all the ways that I could get the first one to be 6 and then get another 6 somewhere. So then, 6, and then the 6 could be the next one, the one after that, the one after that, or the last one. Okay, or the first one could be not a 6, and then I have 6 second, and then the other 6 could happen next. Or it could happen not 6, 6, not 6, 6, not 6. Or not 6, 6, not 6, not 6, 6. Okay? So this next set of 3 things is with the second one to be, first one's not a 6, second one's a 6, and then the other 6 could happen either there, or last. Okay? Okay. Or there aren't that many left. The first 2 could be not 6s, and then I get 6, 6, not 6, or not 6, not 6, 6, not 6, 6. So those are the 2 ways that you could get the first 6 happening the third time, and then the other 6 happens next or last. Or last one, not 6, not 6, not 6, 6, 6. Okay? So obviously that's not, ideally we avoid this, right? It's 10 ways. It's not horrible, but we'd like to have a simpler way to do it. Okay. So let me just do it this kind of long way. And now the logic is that I have 10 different ways that this could happen, and all of them have the same chance. Because this one is 1 6 squared times 5 6 5 6 5 6. Well, this is the same thing, except it's in a different order. 1 6 times 5 6 times 1 6 times 5 6 times 5 6 is still 1 6 squared times 5 6 cubed. Okay? And you can think of that, again, as the probability of one particular sequence. So this is number of ways of doing it, in all these different orders. And this is the probability of one sequence. OK. So any questions about that? OK. So like I said, that's not ideal. I guess I'll erase this. Sort of done with all these rules. So I'd like to have a better way of getting the 10 other than making a list. Okay? So the better way is to use this idea. And I sort of argued here that the number of ways of mixing the 2 f's and the m up is going to be 3 factorial divided by 2 factorial, 1 factorial. Same thing is true here. I can write this as 5 factorial over 2 factorial, 3 factorial, where the 5 is the total number of rolls in this case. This 2 is the number of 6s, and the 3 is the number of non-6s. So I'll call those n's, right? And what does that come out to be? Well, this is equal to 5 factorial is 5 times 4 times 3 times 2 times 1 divided by 2 times 1 and 3 times 2 times 1. Okay? So 3, 3, 2, 2, those cancel. All the stuff over there cancels. And I get 5 times 4, which is 20, divided by 2, 10. Okay? So it works. I sort of try to convince you by using this argument in terms of the mixing, but I do like to do one where it's fairly long. I think with 3 and 2, it's a little bit hard to see that it necessarily works, but hopefully this illustrates a little bit better that it should work for larger numbers. Okay, so the quicker way to do this problem is just to jump to this idea. 5 factorial is the total number of things in your list, and then number of one of them, number of the other one. Do all that. That gives you a quick way of counting what goes out in front, and then the rest of it is just finding the probability of one particular sequence. Okay? Questions? Thoughts? Okay. So let me do one where it's going to be bigger, and I won't write down the numbers. Probability of 5 heads in 10 coin tosses. And then also, actually, before I do that, I'm sorry. Let me write down the general formula. Then I'll do the bigger example. So when is this useful? This is useful if we want to find the probability of, in a particular situation. Oops, formula. So why is it called binomial? The reason why it's called binomial is bi means 2, right? And there are 2 categories of things. So this is typically done in terms of just sort of successes or failures. Okay? So if you have for n independent trials, each with probability p of success, the probability of exactly k successes is n factorial over k factorial n minus k factorial. Hopefully this is, you can read this, p to the k times 1 minus p to the n minus k. It's kind of messy looking formula. So again, I'll talk through it. So this thing out in front, the n factorial, k factorial, n minus k factorial, that's a way of counting the number of things that can happen, the number of different ways of mixing things up. This is the probability of one particular sequence. So it's like, this is like success, 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 k times. And then failure, 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 n minus k times. Right, so that's the way I think about this particular part of it. In order to get k successes in a row, that's like p times p times p times p times p, k times. Just like in the dice example, I have 1/6 squared is the probability of 6, 6, 2 successes in a row. 5, 6 cubed is the chance of getting not 6, not 6, not 6. Okay, it's like 3 failures in a row. Okay? And they have to add up to n. You have a total of n trials. So when I say trial, it's like die rolls, coin tosses, anything where all of them have to be independent. You know, what happens on some die rolls doesn't affect the other die rolls. But other than that, that's sort of what we mean by the word trial. It's these like independent little coin tosses or die rolls or whatever. Yeah, so that part tells you the probability of that particular sequence, but they didn't have to happen in that order. They could have happened in this many different orders. So essentially, what this formula is doing is it's adding this thing up this many times, just like here, right? Each one of those has chance 1/6 squared times 5/6 cubed, and we just add them up 10 times. So this tells us how many times we need to add them up, which is essentially multiplication, right? OK, questions about that formula? OK, so let me write it bigger. I'll just write it bigger real quick in case it's hard to see. Yeah, scrunch down there. So it's n factorial over k factorial, n minus k factorial, p to the k, 1 minus p to the n minus k. And now I want to find the chance of 5 heads in 10 coin tosses. OK, so I'll just translate into these n's and k's. N is the number of trials, so n equals 10. That's the number of coin tosses. K is 5. That's the number of heads that I want to get. And p is 1/2. Right? Then I just plug into this formula. So I get 10 factorial, right? N factorial, 5 factorial. And one way to think about this is that this is the number of tails, right? N minus k is the number of tails. So if you want, you could write 10 minus 5. I'll just write 5. Okay? And then p to the k, 1/2 to the 5 times. This is just, the chance of a tail. I'll write it as 1 minus 1/2 since that's what the formula does. But really, this is just a half, right? It's just the chance of a tail. That's also to the 5th power. Or if you want, you can do it as 10 minus 5. OK, so again, this is like heads, 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 tails, 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 tails. So I'm writing out the probability of that particular sequence and multiplying it by all the different ways that I could have mixed those up in a different order. Okay? And this comes out to be about 0.246. So that sometimes surprises people that it's a little bit lower than you might think. I don't know. This is sort of what we would expect to have happen in 10 coin tosses, but lots of other things could happen. So the chance of that is about 1/4. OK, questions on that? OK, so I want to talk a little bit about the next couple weeks before the midterm. Midterm is in 2 weeks. This is the end of all the material that I'll cover on the midterm. So we'll have 3 lectures of review and problems and whatnot. So I'm a little bit ahead of the syllabus. I'm basically ahead by about a lecture on the syllabus. I think what I'm going to do on March 4th, so you may have heard that March 4th is a sort of day of protest and basically activities against the, budget cuts in education in general. Specifically UC, but statewide, lots of protests and activity and stuff. So I think my plan right now is to be here and answer any questions. It's the last lecture for the midterm, so I don't want to call off lecture. But I also sort of want to leave it available to you to do other things if you want to. So my plan is to do sort of a little bit more structured review and problems Thursday and next Tuesday, and then just sort of I'll be here to answer questions on March 4th. OK? That's my current plan. It's possible that I'll decide that I don't want to be here. And so if I do that, I'll make sure I announce it on BSpace in a lecture. But my current plan is to be here. OK? All right. Bye. See you Thursday.